So, yeah, this talk basically deals with, as the title says, collecting malware, building up huge piles of malware, and then doing something useful with this huge piles of malware. So, brief introduction of myself. I'm Georg Wisiewski. I'm a developer at the mwcollect.org community. I'm member of the Giraffe HoneyNet project, which is a subdivision of the global HoneyNet project dealing with the low interaction honeypot type of stuff. I'm employee of MZSoft. This is a small Austrian antivirus company, and I am student of the RWTH Aachen in Germany. So let's first talk about why we are going to do this and what is our interest in collecting malware. The basic idea is we want to monitor the bad guys and fight them, and especially bad guys here is botnets and botnet herders. And we do this by collecting and acquiring the malware through different means like low interaction honeypots like Nepenthes or Honeytrap, client-side honeypots like pHoneyC, which I'm going to introduce for the first time to the public today, and simple spam traps collecting email attachments like SpamSync. We then have all this malware, and this doesn't help us much alone, so we need to automatically analyze this malware. We're using some standard sandboxes like the Anubis sandbox, but you could also use the CW sandbox or the normal sandbox. We have experimented with Halvor's VX class. He's going to present on it, I guess, later today. And we also developed some custom hash functions for grouping different malware binaries into specimen groups called PE-hash. After analyzing these binaries and having some information what these binaries actually do, we're monitoring the botnets these malware connects to using some monitoring software, and we inform abuse departments and the like. And after doing all that monitoring stuff, we correlate all data like link botnets to binaries and botnets to attacks and all the like, and want to display it in a usable way. So because visualization is also very important, especially for the technically not so skilled. Having all these ideas, what we want to do, this is a picture of an actual setup in the MW-Collect Alliance. So we actually have the malware collection stuff here, putting it all into a database where it's get fetched by the sandbox and some antivirus for having some nice signature names for these binaries. Which is again put into the database. From there, the botnet monitoring software gets the data from the database, again puts it into this, and then we have the web interface for displaying all this. So there's one central database and all these tools fetching data from it. So the first step is the malware collection, and there's several tools to do this. I'm going to briefly outline how they work. First of all, there's Nepenthes, a low interaction honeypot, which works by emulating the known vulnerabilities. So, for example, we have the LDAS exploit. There's some public exploits for it, and we just look at the source of these exploits or the information about the vulnerabilities and write some module to emulate these vulnerabilities. Then we, of course, are going to get some exploit from the malware with a payload, like a shellcode. So we analyze the shellcode, and then just download the malware from the infecting host via HTTP, TFTP, whatever the malware uses to propagate. And then we just store it on the hard disk or submit it into the database or whatever. And since this is implemented in C++ using async.io, this is very performant, so you can monitor your whole /16 subnet or whatever your university or something owns with a single commodity hardware machine. So this, of course, unused IP space you're going to put into your honeypot. Yeah, it's released under GPL. It's like out there for 2 years now, and version 0.2.1 is going to be released soon with some improvements. And main parts of the software are written by Paul Becher and Markus Kötter, and you can just download it for free on the internet. So this is the actual structure of this program. We have these vulnerability modules here that all feed the payload of the exploits to the shellcode manager, which glues these modules with the shellcode analyzation modules. I'm going to explain all of these modules later on. So there's signature-based and also emulation-based shellcode analysis. We, of course, may have to emulate a shell because a lot of the malware uses the bind shell or connect back shell exploits just posted on milworm.com or something. So we have to emulate a Windows shell for these to propagate because they actually exploit a host and then connect to the bind shell used in the exploit and then issue commands, and that's the way to propagate, so they have no real propagation shellcode. And after analyzing this, we get some kind of URL, which is then fed to the download manager, which is the glue between the shellcode modules and the download modules. And at the end of all this, we have a binary we can put on the local hard disk, automatically submit to some Norman sandbox or whatever, or just submit it to some central place via HTTPS. So vulnerability modules, how do they work? They real poorly simulate the original vulnerability. And most vulnerabilities just work in the way that, or most exploits work in the way that you send n fixed strings called stages, and then just expect some response, and this goes on for, I don't know, 2 or 3 times, and then you send your final payload with the offset and the actual shellcode. And these pure simulations, which are sufficient to work with current malware, just send random junk for all these stages the exploit expect, dismiss all the intermediate stages the exploit just needs to set up the actual vulnerability trigger. And we just take into account the last stage, which includes the payload. Then we either pass the whole payload to the shellcode analyzation modules or just a fixed substring in these modules, because there's the shellcode, and that's what we're interested in. So here's one code excerpt. So as you can see, this really all repli is just ½ kilobyte. We're just filling it up with random junk and sending this to the malware. And as they're using these public exploits, this isn't a problem, so we don't need more accurate emulation, so this is really simple. But we do need to sometimes adjust some fixed string somewhere so it detects the right target, like to distinguish whether this is a Windows XP or Windows 2000 host or something like that. But usually it's just as simple as sending random junk, some fixed size junk. And then if we are lucky, we actually get the payload from the malware, and then we can analyze the payload for the shellcode. And there's 2 modules. The first one is shellcode signature, which works like the common antivirus software today. It got patterns for the usually occurring shellcodes, and then in these patterns, these are PCRE patterns. It has certain parameters like which host to connect to a back, or which ports to bind the shell to, or for the simple decoder shellcode parts, there's just a XOR key or whatever. And since patterns are separated into at once the decoder patterns and also the payload patterns, it is really simple to using some, like, I guess it's like 40 different shellcode patterns, and with these you can analyze all shellcode that are out there in malware today for propagation. So that's sufficient. And then there's a shell emulation, because as I've said, most malware today uses just some stock bind shell exploit, which then this shell emulation just opens the port on the given bind shell port, and the malware then issues some Windows bash, I don't know, the batch commands, like echo open blah blah into some file, and then executes the stock Windows FTP command line utility on this file, and the shell emulation all interprets these commands and then builds us a nice URL to fetch the malware from these commands. The other shellcode emulation module is based on libemu, which is also a development by the mwcollect.org project. It's a generic x86 emulator which can detect and analyze shellcodes. It's written in C, also by Marcus and Paul. You can download it for free too. It's all GPL. And as you can see, we also can plot fancy graph with this library, so it's a bit more than just analyzing and detecting shellcodes. And this is, for example, from a link bot. So what this actually looks like, this is the control flow graph of the link bot shellcode. And as you can see here, we have some XOR decoder. We then have the usual locating of the kernel library, and by hash lookup, like today's Windows shellcodes work, we resolve some library functions, and then first open the socket here, and then this here is the whole downloading, and then here we have some execution of these functions, where this is again actually only a stop to locate a function, which is then called by several sub-functions in the shellcode. And at the end, I guess it's here, we actually have downloaded the malware, and then again call in here to finally execute some of these functions. Yeah, it's pretty small because the shellcode is rather big, to finally execute the downloaded binary on the infected host. So with this approach, we are able to generically detect arbitrary zero-day shellcodes, so to speak, because it's just a full-blown CPU emulator, and any shellcode that runs on the attacked CPU will also be detected by this one, and we know what it does generically. And this is a new development because, in the past, if there was a new shellcode, some users sent us a new shellcode, we had to analyze it manually in some debugger or disassembler, write a new pattern, and this took time, and this just works immediately because it's generic. And then after we build our nice URL from the shellcode, we're just going to download it because they usually use either HTTP or FTP. Some other malware variants use TFTP or even RCP. I didn't know Windows had RCP until I saw some malware using it. And sometimes there are also kind of proprietary commands for transferring the malware. Because, for example, Agabot introduced csend and creceive, which are rather simple because they just send the length of the binary and then the binary itself, and that's it. Or link bind and link connect back, which are really, really nasty because these shellcodes actually generate a per session secret. So for each attack, they generate a new secret. And the secret is actually not just put into the shellcode, but there's code generating the secret put into the shellcode. And this then has to be transmitted on we want to download the malware binary connection. And if the secret is not right, the bot just terminates the connection, and otherwise it works. So this was actually a measurement against this kind of honeypots, low interaction honeypots, but as we could write patterns for this too, we could easily circumvent this. But it required some time of research to see why does it generate this junk in memory, and why does it sometimes terminate connections and whatever, till we figured out, okay, this is kind of a per session secret we have to transmit. And also for HTTP and FTP, we first used libcurl, which didn't work out all the time because we had to write RFC and compliant implementations of these two protocols, because the Windows implementations of these protocols were also RFC and compliant. So if you use the FTP stock FTP command line client, it allows you to do things the normal FTP RFC doesn't allow you to do. And the bots actually were just developed using these command line tools from Windows, and so I guess the bot authors never read any RFCs. So we had to write some broken implementations that are as broken as the Windows implementation, so they would actually work with the malware. So we again had to re-implement these protocols, which was a tedious work. Well, we had to do it. And that's about it. So as I've said before, there's some alliance, the MW collect alliance, and this is you can get a picture of what is going on in the world using the pentest centers from this. So as you can see, even though client exploits are today said to be the way to go, this is from this week a picture. So there's still malware spreading using the traditional exploits, and the pentest can catch all over in the world. So red balloons are attacking hosts, and green balloons are sensors. You can see there's malware everywhere, basically. That was a bit about Nepentest, so let's have a look at some other kind of malware collection tools. PHoneyC is a low interaction client honeypot, because nowadays, most of you probably know MPEG or IcePack. There are client-side exploit toolkits, and it's a big trend because there are way few vulnerabilities like newcomer that are exploited remotely without any setup published anymore today, and most vulnerabilities are in Internet Explorer whatsoever. So Nepenthes was cool like 2 years ago, where everything spread through decom, and nowadays we need to actually find the exploits. So the attacking hosts aren't coming to us anymore. They're not knocking at our door and saying, I want to attack you. But instead, we have to spider the web and find a malicious website. And this is what this software does. So it's not released yet because there's still some work in progress being done on it. And it's written in Python, mainly by Jose Nazario, who's working for our networks. And we're collaborating on this. So it spiders the web like a search engine looking for attacking sites. And to find actually attacking sites, what we do is we deobfuscate all this JavaScript, which is often pretty much obfuscated, and then again just run the libemo shellcode detector on it. So yeah, if there is an exploit in this JavaScript, there's going to be some variable holding the actual shellcode used in that exploit, if it's not like cross-site domain, cross-domain scripting vulnerability. And for these, there are static modules detecting these kinds of vulnerabilities, similar to Nepenthes. And this way, we can find malicious websites. And as you know, there's already high interaction client-side honeypots, and this is an ideal pre-filter because running each site on the web through a high interaction client-side honeypot takes like, I don't know, one minute per site or something. And using this, we can spider the web really fast, and suspicious URLs can be then forwarded to a high interaction client honeypot, speeding this up a whole lot. We want to make this even cooler by downloading the malware automatically from these sites instead of feeding them to a high interaction honeypot like we do in Nepenthes right now, because with libemu we already have the capability to see what is the shellcode actually doing, and if we have this capability to see what it's doing, why not download the malware directly in the low interaction honeypot? And this would then be a real cool thing then, because it's very fast and gets you all the malware. So how does it work? We have a URL, we fetch the malware and all reference resources. We deobfuscate the included JavaScript, which is often like several nested eval commands for those of you who know JavaScript. Then we just run it through libemo or look for certain cross-domain scripting vulnerabilities like in the old ages of Internet Explorer and something like that. And this is actually from a very recent Internet Explorer exploit, where it just has a shellcode, which is a Perl script, which has a shellcode, but then it writes a JavaScript file, which then calls just an unescape on the shellcode. So in the end, you will just have the actual shellcode as a parameter to the function in JavaScript, and using SpiderMonkey, we can just look at all variables and parameters, and then use libemo to see, okay, this one is a shellcode, this is what we are interested in. Another way of finding malware besides the Honey client is just a spam thing, because at least since Stormworm and even before, a lot of malware is just spammed around, and dumb users click on attachments because it's a funny picture or something, or dancing skeleton, and execute it, and well, this is malware interested in too. So what we do is just we set our own up our own mail server. Propagate email addresses to this mail server all on the web, like on some forums or whatever. And then just, this is like dark space for IPs, this is like dark space for mails. So we just consider all email coming to this mail server as malicious. And as a result of this, all executable attachments to this web server are malicious too. So this is the way we can very simply collect these kind of malware. And yeah, this is nothing to be released because there's no real software being developed. It's just setting up your mail server and scanning through all attachments. That's another thing we're doing. And now we've got that huge pile of malware, which was actually what we did in the first year. We just stacked up the malware and we're happy we had so much malware, but we want to put some use to all this malware we were collecting. So we're doing some malware analysis. We're working together with the folks from the TU Wien here in Vienna. They developed the Anubis sandbox, which is pretty simple. It's just like a kernel rootkit running in a virtual machine. So you load that malware into the virtual machine. This kernel rootkit records all calls to APIs and therefore knows what the malware does. So yeah, what you get in the end is a detailed report on what the malware does. So what we are especially interested in is like this here joins IRC network, and this is just the header of the whole page. So it goes like 20 or 30 pages long, and then we can see the detailed information where it's connecting to, which works for, at the moment, not so many IRC binaries, but it works at least for some. So this takes the burden of manual analysis away from us. Yeah, and then we got these reports, and we wrote some parser script for these reports, and what we get in the end is just a huge database of botnets. So we have a binary here, and here's the botnet. So this is actually botnet command and control host. Here's the part, no server password. This is the channel with the channel key, the server nickname, username, and real name. And this goes on for, this is just like, I just attached to the screen where this analyzation script was running and then copied it. So as you see, for some binaries there's also no botnet information, but it's just a whole lot of botnet samples we're seeing, and yeah, we just fetch it out of them. And yeah, well, that's about it for getting all the botnet information, which we are going to use later. And another problem in malware analysis we were running into was polymorphic binaries. So for those of you who know the all-APL worm, it's polymorphic. So each attack yields to a new binary with a new unique MD5 sum. And that's pretty nasty because this is a screenshot from the web interface, which was just displaying the most recent binaries. And as you can see here, these all just hit our sensors once, and these were all APLs, and these just pollute our database because, you know, it's pretty hard to work with a database which we're seeing like, okay, there's like 100 new binaries today. What does this actually mean? Was there 100 new botnets created today in one single day, or was it just one polymorphic binary attacking you once again? And what we did is develop a custom hash function, because there's a lot of nice algorithms to group malware binaries into specimens, for example, VX class, but these probably take like 10 minutes per binary. Again, this is taken from VX class, which is a great thing, but we get at peak times 10 binaries per minute, and this is, well, doesn't match by a factor of 100, so it's too slow by a factor of 100. And we need a way faster method to actually group binaries together into specimens. And what we do is we look at the actual PE structure of these binaries, and we developed a hash function that just inspects the PE headers. And therefore, polymorphic binaries always share the same basic PE characteristics, and this way we can identify them and group them together by this specific hash function, hash value in this case. So we hash the PE header, and yeah, we can group them by the hash value as if it was the MD5 value of the whole binary. So we can say this is one malware specimen, this is one malware signature name or whatever. And it's important to note that the result of this research is a hash function and not a message digit. So it's very trivial for an attacker to construct two binaries which entirely different content which share the same hash value, because it's a hash function and not a message digit. It's a cryptographic difference. So first, security by obscurity applies. So if we tell attackers how our hash function works, they can just construct collisions and therefore circumvent our research. And we must be very careful when publishing these hash values. So when we say we have a new malware specimen with this hash, this might have some consequences. So it's better to MD5 the actual hash value again, so an attacker cannot reverse the hash function to the PE properties. Yeah, and this hash implementation is made by me, was my research, and if there's some interest, yeah, please.
A small question, why don't we use MD5 in the first place for hashing?
Well, we actually do, but so for the web interface, we actually use MD5 hash because the hash function is very long and we compress it that way. But the actual hash function itself is very, I just wanted to say that it is easy to create collisions this way. So we must make a secret of our hash function to prevent collisions. And yeah, what we first look at is the actual subsystem or whatever, the stack size and the imported libraries. These are global PE properties, and these are very specific sometimes. In other cases, stack and heap size is constant for certain compilers. So these are just some basic measurements, and the more interesting things we are looking at is the properties of the actual sections. So if you don't know PE files, so for those who don't even know that, PE files are the executable file format of Windows. And like ELF is for Linux. And we're looking at data section and code section and the like. And we are actually only looking at the first 3 sections because otherwise the hash wouldn't have a constant length. We look at the size of the sections in the executable, where it's going to be loaded in the memory. These are very different for each binary. We XOR the hash names. For some compilers, we XOR hash the names of the sections. For some compilers, these are static. For other malware specimens, these are dynamic with each instance. With each specimen, not with each instance. And what is very important, because we still had some collisions for different specimens, is we approximate the Kolmogorov complexity, which is a theoretical measurement in computer science for the richness of information. So if you want to say 6As is way simpler in the richness of information terms than this random string, then you do this by Kolmogorov complexity. And to approximate this, because from definition this cannot be generically computed, we approximate it by compressing the data and then just look at the ratio of the compression, which is a good approximate of the richness of the data, because if you have a lot of A's, one like 4 kilobytes of A's, you can compress it to a few bytes. And if you have 4 kilobytes of random data, you can't compress it at all, more or less. And this is our approximate of the richness of the data, which we scale down to an index between 0 and 7. And this way, we can easily say, for example, this is code, or this is some zero initialized data or something like this. And the funny thing is, even if we have a metamorphic malware specimen, which transforms its code, each which is even worse to detect than polymorphic malware, the richness stays the same. Even if all instructions change, the richness more or less stays the same. So this is a very good measurement for this. And the results from real life showed us that this hash function we developed actually works, because there's 33 distinct PE hash for all apples we ever see. And for all these PE hashes for these all apples, we have exactly 0 collisions with any other kind of malware. And 3 of these hashes were holding more than 99% of all APL, which correlates with 3 different all APL variants discovered by various antivirus companies. And our guess is the remaining 30 hashes, which all were only holding 1 binary, were transfer errors. So there's like 20,000 all APL we've seen so far, and they all have the same hashes except for 30, where we're saying these are simple transfer errors because they have pretty unusual sizes, and some aren't even valid PE files. So this showed us this actually works, and what we have now is this nice grouping of binaries. So as you can see, we now have those with more hits again, and we can group them together and take out all these all APL and such, and so it actually works. And now that we have all the data, we have analyzed the malware and have got some botnet information and whatever, we want to do some botnet monitoring, because most of today's DDoS still comes from botnets, and so we want to be seeing which botnet herder is attacking whom, or where are all these phishing mails coming from and all the like. This is mostly today coming all from botnets, so we do some botnet monitoring. And yeah, we have developed a tool, botsnipd, for the German Federal Ministry of Information Security, I guess is the correct translation, so it's a BSI for the Germans here. And it's also written entirely in C++ for performance using asynchronous I/O. So as you can see, we like performant applications. And the design goal from the BSI is that we monitor 10,000 botnets on, simultaneously on a single commodity hardware server. And this is the approximate of half of all botnets out there in the world. So there's sources saying like there's 20,000 botnets in the world, which is, I guess, even a little bit more than there actually is. But there are these sources, and this is one of the biggest numbers we heard. And with these design goals, we can monitor all botnets on the world with 2 commodity servers. Actually, the software is also shared under the GPL, but not with everyone, because we don't want the black hats to have our software, so they cannot block our monitoring software by looking at its source in case it has any design flaws, revealing its identity at monitoring software. But those who are like ISP or whoever has a reason to monitor botnets can approach us or the BSI and say, we want this software, and they're going to share it under the GPL, so you even get the source with it. They actually allowed me, so this is kind of classified information. It's not really classified, but they want us to talk about it, but they allowed me to talk about it here, so that's pretty nice. And this is how it actually works. This is the core daemon, which is again modularized. So you have the different client modules, because not all botnets are ISC anymore today. Like there's a lot of HTTP botnets in Russia these days, and here in the States, there's still a lot of IRC botnets, and there's also a WovenNet client for monitoring the Stormworm botnet. Yeah, and these are all managed by the protocol manager. So there's an interface to our great Postgres database again, or we can also control this daemon by IRC itself. So as soon as we have a new botnet in the database, we allocate a new client from some protocol, and this then just runs and joins the botnet and feeds all generated events back to the event manager, which again feeds the information into the database. And I guess I have a screenshot from that database later on. And we also have some logging and the normal daemon functions in that daemon. So yeah, this is how the software works, and if you're interested in details or whatever, don't hesitate to approach me, but this is what I can officially, globally, publicly say about it. And so what are we seeing right now? Because it's nice to talk about our theory and software, but it's also nice to talk about results. And what we're seeing is, first of all, starting in Russia these days and coming to other continents more and more is the prevalence of HTTP botnets, because ISC is nice, but you somehow limit yourself. For example, if you have a botnet of a fixed size, you have also that amount of connections to your server simultaneously. So if you have a 60,000 botnet, you have 60,000 simultaneous TCP connections running all the time, which means they are eating up your resources all the time. And an HTTP botnet, in an HTTP botnet, you are just setting up your web server, and each bot pulls your command file like every 60 minutes, and that means you have 60,000 connections, but spread over 60 minutes and not being active all the time, which means on the one hand you have less resources to maintain on the server, on the other hand you have more traffic because there's a handshake for each connection and whatever. And also, it's way easier to set up for the kiddies, because they don't really have to root a server to set up their ISC server. They just have to own some web server. And if they own the web server, they can just set up the command file there and let the bots pull these URLs. So they can actually use some tripod or whatever account, hack it, and then put the command file there. Yeah. As I've said, it's not performant, but it's the way to go for kiddies. And the other thing is peer-to-peer command and control, like seen in Stormworm. And I think has already been talked to death by some researchers, but just briefly introduced here. So they use the overnet peer-to-peer network, which is usually used for file sharing. Frequently query the network for updates, and So the advancement is you have no more one single point of failure. So if you usually want to take down a botnet, you take down this command and control infrastructure, which is between 1 to 10 servers or something like that, and you're done. But with this peer-to-peer approach, you just can't take down all overnet nodes in the world because there's millions. So yeah, these are hard to take down. And overnet as a decision for peer-to-peer protocol is actually a good decision by the malware authors because it features DHT search, which is like nice for finding a central point in the network, so you don't have to float the whole network, but you just ask the network, okay, where is this information, and then you have a short single route in the network. So algorithmically, this is a nice idea to use overnet and not like Nutella or what else. On the other hand, big botnets could also profit from Gruntella because in the Nutella case, you're flooding your commands through the whole network, and each node passes your queries on. The advance here is that if you issue a new command, it gets floated through the whole network at once. And using overnet, you just query through the network, and all nodes query for the same, which means they are going to end up on, I don't know, like 100 nodes in the overnet network are going to be queried all the time because they know where this resource is. And so they're on the default route to your botnet resource, so to say. And in the Gruntella network, your commands just spread out. So for a real big botnet, even bigger than Swarmworm, which is actually not as big as media always says, this would be better. However, if you have a single infected host behind firewalls or whatsoever, using peer-to-peer as command control is very noisy because if you have an infected node with an IRC network, there's one additional TCP connection and that's it. And if you have an infected node which is using peer-to-peer, it's issuing new TCP or UDP connections all the time, and therefore probably putting up pretty much alerts at your firewalls. But again, botnets are usually targeting home users, so people don't bother. I mean, home users don't have firewalls anyway. And the third new trend is encryption of commands for RIC botnets. Because some years ago, you would only have seen these kind of commands. So this is actually a screenshot from the database maintenance tool maintaining the botnet database. You would only see these, I don't know if you can read it, it's like ADV scan, AS1, SMB, and so on to this exploit and which range to scan, and that's it. So these are pretty easy to interpret. Now they use some kind of encryption in some botnets, especially link bot botnets, which, well, it's not a real encryption because it's just rotating some bits with the roll instruction and using then some reverse custom base64 encoding. So it's not real encryption, but merely an obfuscation. But nevertheless, each botnet binary contains some custom constants for this obfuscation. So we can just say, okay, they do this, and to obfuscate the commands, and we can reverse it. But we have to look at each binary manually to figure out which constants for rotation they are actually using. And this is, again, tedious work we wanted to avoid with doing our whole automatic approach. Yeah, and so this is kind of necessity. We're now looking into machine learning for automatically identifying what these commands do with some high interaction honeypots, but this is research we're thinking about to do in the future, so this isn't even ongoing research, and this is one of the current trends we were looking at. Yeah, and that's pretty much it. So we have some conclusion. First, it is feasible and possible to build a setup that collects malware, analyzes it, and monitors botnet without any human intervention from start to the end. So Herder compiles new binary, releases it, and we automatically join the botnet without any human intervention, and this is what we wanted to do. And second conclusion is building up that setup and maintaining it and all that kind of stuff is a shitload of work. So it's easy to put all these software together in a way so it doesn't work at all. And if you don't want to go through all these hassles we went through in the last 2 years, you can just give the MW Collect Alliance a shot, which I've been talking before earlier, because everyone is free to join. This is .org stuff, so if you need malware binaries or botnet information or whatever, feel free to approach us. And if you fulfill the requirement of being some trustworthy person or corporation, you can just join. as long as you guarantee not to share the data with any untrusted parties. That's not a big requirement, I said. Yeah, this is what we're seeing. So like, yeah, this is from this week again. So there's a lot of attacks and even more binaries we're seeing at times. So no, this is different scales, but at some peak hours there's more than 300 binaries an hour. Yeah.
Are these statistics online?
Yeah, just go to that URL and it's all public data. You can just fit it there. Or ask us if you need any polished, specialized graphs or whatever. So, thanks to all the people that make this possible, and also to those that gave us money for making this possible. Because as I've said, we're doing actually this all in our free time. We're students. And any questions?
The botnet monitoring stuff, the one is very interesting. I was wondering, are you planning to execute the client somehow and monitor?
No, actually this is what we wanted to avoid. So we built this whole setup to avoid this, executing the actual client, because we're using this existing sandboxing and also researching some more static analysis stuff. We want to exactly identify the protocol it is using and use then our custom tools to monitor the botnet. Because if you execute the client in some environment, first you run into hassles if you are carrying out an actual DDoS attack and your IP is participating. Well, you can still place firewalls around it and that's fine. But the second thing is we are monitoring with this over 1,000 botnets constantly, and it's getting more or less, and it's going to be much more in the future. Not because there's going to be much more botnets, but we're not seeing all botnets right now. And if you monitor these by executing them, you need a virtual machine for each of them. And I mean, if you pay us money for running 1,000 parallel hosts for monitoring them, that's fine. We're going to do it because it's the simplest for us. But we don't have money, so we have to be creative, and this is what we came up with.
Okay, but the part I don't understand is how do you actually get the traffic from this?
I'm sorry, I didn't understand you.
How do you get the traffic? So how do you collect? So you have,
The traffic itself, yeah, the botnet traffic, you mean? Yeah, we actually have the client modules here that interpret the traffic, so they analyze it and then parse it for IC or HTTP, and the actual traffic payload, so the IC priv messages or whatever, is then stored in this database. As you can see, these are botnet commands and then stored in the database. That's it. Any other questions? All right, I said that's it then.